Take a deep breath and feel the weight of your body as it sinks into the soft, welcoming embrace of your bed. Allow your thoughts to drift like stardust, settling into a state of quiet observation as we begin our journey into the velvet dark. High above the atmosphere of Earth, far beyond the reach of the wind and the clouds, the universe operates on a scale of precision that rivals the finest Swiss watch. We are traveling tonight to witness one of the most remarkable timekeepers in the cosmos, the pulsar. In 1967, a young astrophysicist named Jocelyn Bell Burnell sat in a quiet room in Cambridge, looking at miles of paper charts, when she noticed something strange, a bit of scruff that appeared at the same time every night. This was the discovery of PSRB 1000, 919 plus 21, the first pulsar ever recorded, located in the constellation of Vulpecula. It emitted a radio pulse every 1.337 seconds, a rhythm so steady and so perfect that for a brief moment, scientists wondered if they had finally heard the heartbeat of an alien civilization. But the reality was even more poetic. What they had found was the ghost of a dead star, a remnant of a supernova that had collapsed under its own weight, leaving behind a sphere of matter so dense it defies human comprehension. Imagine, as you float through the void, that you are approaching one of these celestial lighthouses. Despite containing more mass than our entire Sun, approximately 1.4 times the mass of our solar center, the pulsar is incredibly small. It is a sphere only about 20 kilometers, or 12 miles, in diameter. If you were to place it on Earth, it would fit neatly within the borders of a single city like Manhattan or London. Yet, within that small, city-sized space, the mass of a giant star is compressed until the atoms themselves break, leaving only a soup of neutrons. Consider the texture of this object. As you drift closer, you wouldn't see a burning ball of gas like our Sunday. Instead, you would see a surface that is perhaps the smoothest and hardest in the universe. The crust of a pulsar is made of iron nuclei arranged in a rigid crystalline lattice, 1 billion times stronger than steel. This iron isn't like the metal we know on Earth. It is an ultra-dense polymer, crushed by gravity that is 200 billion times stronger than the pull you feel right now against your mattress. Because of this intense gravity, any mountains on the surface of a pulsar are less than a millimeter tall. Imagine a sphere the size of a city, polished to a mirror shine, with imperfections no thicker than a sheet of paper. It is a world of absolute, terrifying smoothness, spinning in the silence of space. You might feel a subtle vibration in the fabric of space-time as we observe the spin. This is the conservation of angular momentum. Just as an ice skater spins faster when they pull their arms close to their body, a star that was once millions of miles wide spins faster and faster as it collapses down to those 20 kilometers. The Crab pulsar, located at the heart of the Crab Nebula some 6,500 light-years away, rotates 30 times every single second. Imagine a city, with all its weight and mass, spinning as fast as the blades of a kitchen blender. It is a rhythmic, mechanical thrumming that anchors the galaxy. As we float in the weightless dark, let's consider the temperature of this cosmic clock. While the space around it is a frigid negative 270.45 degrees Celsius, the pulsar itself is white hot from its violent birth. A young pulsar can have a surface temperature of 1 million Kelvin. However, because it is so small, it cools very slowly, radiating its heat into the void over millions of years. You can almost feel the phantom warmth of that distant fire, a glow that has persisted since the star exploded thousands of years ago. The pulsar is surrounded by an atmosphere that is uniquely strange. Because the gravity is so intense, the atmosphere is incredibly thin, only about 10 centimeters deep. Within those 4 inches of air, atoms of carbon and helium are squeezed into exotic states of matter. Above this thin veil lies the magnetosphere, a region of space dominated by a magnetic field that is 1 trillion times stronger than Earth's. Earth's magnetic field is about 0.5 Gauss, enough to gently turn a compass needle. The magnetic field of a pulsar can reach 10 to the 12th power Gauss. This field is so strong that it distorts the very shape of atoms, stretching them into long, thin needles. The sound of a pulsar, if we were to translate its radio waves into something we could hear, is a steady, rhythmic ticking. It is the lighthouse effect. The pulsar has two beams of intense radiation shooting out from its magnetic poles composed of radio waves, X-rays, and even gamma rays. Because the magnetic poles don't always line up with the axis of rotation, these beams sweep across the universe like the light from a lighthouse. Every time the beam passes over Earth, our telescopes record a pulse. For the fastest known pulsar, PSR J1748-2446 AD, this happens 716 times every second. It is a hum, a sustained note in the grand orchestra of the cosmos, spinning at 24% the speed of light at its equator. Focus now on the density, for it is here that the pulsar becomes truly meditative. If you were to take a single teaspoon of pulsar material, it would weigh approximately 5 billion tons. That is roughly the weight of every human being currently living on Earth, plus the weight of every car, truck, and bus, all condensed into a small silver spoon. This density is made possible by neutron degeneracy pressure, a quantum mechanical effect that prevents the star from collapsing further into a black hole. It is a delicate balance, the inward crush of gravity fighting against the outward pressure of subatomic particles. It is the ultimate stillness born from ultimate pressure. You might wonder what it would feel like to be near such an object, protected by the safety of your imagination. You would feel the immense tidal forces, a gentle tugging on your toes and head as the gravity tries to stretch you into a thin line, a process physicists call spaghettification. But here, in our story, we are mere observers, weightless and unaffected. We feel only the rhythm. The pulsar is the most stable clock in the universe. Some pulsars are so precise that they lose only 1 second every 100 million years. They are more accurate than the atomic clocks we use on Earth to synchronize our GPS satellites and our internet. In the 1970s, the Voyager 1 and 2 spacecraft were launched into the deep, carrying a golden record. On that record is a map of our location in the galaxy, defined by the positions and timings of 14 different pulsars. We have used these spinning stars as our celestial landmarks, our "You Are Here" sign in the vastness of the Milky Way. They are our guides through the dark, their steady one. 3-3, second or 0. 0-3-3, second pulses, acting as beacons for any traveler who might one day find our message. As you settle deeper into your pillows, imagine the light of the Crab pulsar. It was born in the year 1054 AD, when Chinese astronomers looked up and saw a guest star, so bright it was visible during the day for 23 days. That explosion left behind a cloud of gas and dust 6 light-years wide, and at its center, the pulsar we study today. Every pulse we receive now began its journey 6,500 years ago, traveling through the vacuum of space at 299,792 kilometers per second, just to reach our eyes and our instruments. The colors of the surrounding nebula are a soft, glowing palette of reds and blues. The red comes from ionized hydrogen, while the blue is synchrotron radiation light produced by electrons spiraling at nearly the speed of light around those trillion Gauss magnetic field lines. It is a soft, ethereal glow, like a neon sign flickering in the distance of a lonely highway. The pulsar itself sits in a wind nebula, where it sheds particles and energy into the surrounding space, creating ripples and waves in the gas like a stone dropped into a still pond. Sometimes a pulsar experiences what scientists call a glitch. For a brief moment, the pulsar's rotation suddenly speeds up. This is thought to be caused by starquakes, where the rigid iron crust of the pulsar cracks and shifts by a fraction of a millimeter, or by the movement of superfluid neutrons deep within the core. Even in the most perfect clocks of the universe, there is a moment of adjustment, a small breath of change, before it returns to its steady, eternal rhythm. Think of the pulsar as a heart. It is the dense, heavy, beating heart of a fallen giant. It does not sleep, it does not tire. It simply spins, marking the passage of eons with the precision of a master craftsman. The escape velocity on the surface of such an object is 150,000 kilometers per second, half the speed of light. Nothing that lands there can ever leave, yet the light it emits travels across the entire universe, carrying the news of its existence to the furthest reaches of space. You are drifting now, much like the radio waves from PSR B 1000 919 plus 21, moving through the silent gaps between stars. The universe is not a place of chaos, but a place of profound order. Every atom in your body was once forged in the heart of a star, perhaps one that ended its life in the very supernova that created a pulsar. You are connected to this clockwork. The same laws of physics that govern the 716 per second spin of J1748-2446 govern the steady rise and fall of your chest as you breathe. The pulsar is a reminder that even in the aftermath of a great collapse, something beautiful and permanent remains. It is the comforting void. It is the silence that follows the roar of a supernova. As we continue to drift, the pulses become a background hum, a lullaby of physics and time, guiding us further away from the noise of the world and deeper into the stillness of the cosmic night. Feel the coolness of the vacuum, the warmth of the distant starfire, and the absolute reliability of the spin. You are safe in the hands of the universe's most perfect timepiece. Your journey has only just begun, and the rhythm will carry you through the dark. Moving through the velvet stillness of the cosmic night, we find ourselves tracing the invisible lines of history that connect our human curiosity to the rhythmic beating of these stellar remnants. While we float in this weightless environment, suspended in a sea of silent energy, it is worth reflecting on how we came to understand these master timekeepers. Long before we had the technology to see them, the existence of such dense objects was a whisper in the minds of theorists. In 1934, a mere 2 years after the discovery of the neutron, two visionary astronomers named Walter Baade and Fritz Zwicky sat in their offices at the California Institute of Technology and proposed a radical new concept. They suggested that when a massive star exhausts its fuel and collapses in a supernova, it might leave behind a core composed entirely of neutrons. This was a theoretical ghost, a mathematical possibility that wouldn't be physically verified for more than 3 decades. Observe the patient passage of time as we move from that early prediction to the late 1960s. At this very moment in our journey, we are approaching the constellation of Vulpecula, the Fox. It was here, in 1967, that Jocelyn Bell Burnell, working under Anthony Hewish at the Mullard Radio Astronomy Observatory, noticed a signal so regular it seemed artificial. She dubbed the source LGM1, standing for Little Green Men 1, because the pulse was so steady it defied any known natural explanation at the time. This source, now officially catalogued as PSR B 1919 plus 21, emitted a burst of radio waves every 1.337 seconds. As you visualize this, imagine a steady, rhythmic pulse in the darkness, a metronome set by a star that has become something entirely new. Picture this. The pulsar is like a grand mechanical clock housed in a silent cosmic cathedral. In 1968, shortly after Bell Burnell's discovery, the astrophysicist Thomas Gold published a paper in the journal Nature that finally solved the mystery. He correctly identified pulsars as rapidly rotating neutron stars. Around the same time, Franco Pacini suggested that a highly magnetized, spinning neutron star would emit electromagnetic radiation, confirming the mechanics behind the lighthouse effect we observe. We are witnessing the legacy of these minds as we glide through the silent void, watching the beams of light sweep across the vacuum with unfailing regularity. What's happening now is a shift in our perspective, moving from single stars to the dance of pairs. In 1974, Russell Hulse and Joseph Taylor used the Arecibo Observatory in Puerto Rico, a massive 305-meter radio dish nestled in a natural sinkhole, to discover the first binary pulsar, PSR B 1913 plus 16. This system consists of a pulsar and a companion neutron star orbiting each other in a tight 8-hour cycle. Notice the slow, graceful spiral of their motion. Scientists discovered that the two stars are drawing closer together by about 3.5 meters every single year. This occurs because the system is losing energy in the form of gravitational waves, ripples in the very fabric of space-time. This observation provided the first indirect evidence for the existence of gravitational waves, confirming Albert Einstein's general theory of relativity with a precision better than 0.2%. For this monumental work, Hulse and Taylor were awarded the Nobel Prize in Physics in 1993. At this very moment, we can sense the gravity of these objects pulling gently at our consciousness. Consider the sheer scale of the energy involved. In 1971, the Uhuru satellite, the first dedicated X-ray astronomy mission, discovered the first X-ray pulsar, Centaurus X3. Unlike the radio pulsars that spin down as they age, X-ray pulsars like Centaurus X3 are often recycled. They inhabit binary systems where they siphon gas off a companion star. This infalling material forms an accretion disk, glowing at temperatures of millions of degrees, and as the gas lands on the pulsar's surface, it transfers its angular momentum. This process acts like a giant cosmic hand pushing a playground merry-go-round, spinning the pulsar up to incredible speeds. Deep within the heart of the galaxy, we find the most extreme examples of this recycling process, the Millisecond Pulsars. In 1982, astronomer Don Backer and his colleagues discovered PSR B1000, 937 plus 21. This pulsar rotates 642 times every second. To put that in perspective, the surface of this city-sized star is moving at roughly 14% the speed of light. It is a dizzying, yet perfectly stable rotation. These objects are so old, often billions of years, that they have been spun up to these speeds over eons, becoming the most precise clocks in existence. There is a unique beauty in the colors of the radiation these stars emit. While we cannot see radio waves with our eyes, we can visualize them as soft, rhythmic undulations of blue and violet light. In 1992, Alexander Vulshan and Dale Frail used the Arecibo telescope to look at pulsar PSR B 1257 plus 12. What they found changed our understanding of the universe forever. They discovered 3 planets orbiting this dead star. These were the first exoplanets ever confirmed to exist outside our solar system. Imagine these worlds named Drauga, Poltergeist, and Phobetor bathed in the intense radiation of their pulsar host. Drauga, the innermost planet, has a mass only twice that of our Moon, while Poltergeist and Phobetor are roughly 4 times the mass of Earth. They are ghost worlds, survivors of a supernova, orbiting a star that is essentially a giant atomic nucleus. Notice how the universe preserves its history in these pulses. The Vela pulsar, located approximately 960 light-years from Earth, is the remnant of a supernova that occurred about 11,000 years ago. It rotates about 11 times a second, or every 89 milliseconds. When we look at the Vela pulsar, we are seeing a snapshot of a catastrophe that our ancestors might have witnessed in the night sky at the dawn of human civilization. The nebula surrounding it is a chaotic tapestry of filaments, glowing in the soft light of ionized gases, expanding outward into the cold dark. Scientists discovered that some pulsars possess magnetic fields so intense they deserve their own classification, magnetars. A typical pulsar has a magnetic field of 1 trillion Gauss, but a magnetar, like SGR 1806-20, has a field 1,000 times stronger than that, reaching 10 to the 15th power Gauss. If a magnetar were to pass within 100,000 miles of Earth, its magnetic field would instantly erase the data on every credit card on the planet and pull the very atoms of your body into needle-thin shapes. Yet, from our safe vantage point in the quiet void, we see only the shimmering distortion of light as it passes through these immense fields, a subtle warping of the star field behind the pulsar. Consider the rhythm of a pulsar glitch. In 1969, astronomers first observed a sudden increase in the rotation speed of the Crab pulsar. This was a deviation from its steady slowdown of about 4.2 times 10 to the minus 13 seconds per second. These glitches are like the heartbeat of the star skipping a beat. They reveal the interior structure of the pulsar, which scientists believe contains a superfluid of neutrons. This fluid, which has 0 friction, can rotate independently of the pulsar's crust. When the two catch up to one another, a glitch occurs. It is a moment of internal realignment, a settling of the star's very soul before it continues its eternal, rhythmic spin. Deep within the silence, we can reflect on the concept of pulsar timing arrays. By monitoring a network of millisecond pulsars across the galaxy, astronomers are creating a galactic-scale gravitational wave detector. They look for infinitesimal changes in the arrival time of pulses changes, as small as a few billionths of a second. This allows them to detect the low-frequency hum of the entire universe, the background vibration caused by pairs of supermassive black holes orbiting each other in the hearts of distant galaxies. We are essentially using the galaxy as a giant ear, listening to the deepest chords of space-time. As we continue our slow, weightless travel through this narrative, let the history of these discoveries settle over you like a warm blanket. From the 1,934 predictions of Bade and Zwicky to the 1,992 discovery of the first alien worlds, the story of pulsars is a story of human persistence. It is a testament to our ability to find order in the dark, to hear a heartbeat in the radio noise of the cosmos. The pulsar is not just a dead star, it is an anchor. It is a fixed point in an ever-changing universe, a lighthouse for the mind. Notice how the light from these distant beacons doesn't just illuminate the space around them, it illuminates our history. Each pulse is a message from the past, a steady "I am here" that has traveled for thousands of years. The Crab pulsar, for instance, is the central engine of its nebula, pumping out enough energy to light up a cloud of gas 6 light-years across. It is a dynamo, a spinning weight of 1.4 solar masses, turning mechanical energy into light and heat. Feel the stillness of the void around you. In the absence of an atmosphere, there is no sound, only the internal rhythm of your own heart, mimicking the steady tick-tick-tick of the pulsar. This is the clockwork of the heavens, a system governed by laws that are as elegant as they are absolute. We are observers in a gallery of giants, watching the slow, rhythmic rotation of the universe's most perfect machines. Let the steady frequency of the pulsar act as a tether, keeping you grounded in the peace of the present moment while your mind explores the infinite reaches of the past. The spin is gentle, the time is vast, and you are perfectly safe in the embrace of the cosmic dark. Imagine the weight of a simple paperclip resting in the palm of your hand. It is light, almost non-existent. Now, try to envision that same small object possessing the mass of a large freighter ship. This shift in scale is the first step toward understanding the profound density of the pulsar you are currently observing from your position of weightless safety. As we glissade through the ink-black silence, consider that a single sugar cube of pulsar material, a tiny volume of 1 cubic centimeter, would weigh approximately 1 billion tons. To give that number a home in your mind, imagine taking Mount Everest, with all its granite, ice, and ancient stone, and compressing its entire bulk until it fits inside that 1 centimeter cube. This density, measured at roughly 10 to the 17th power kilograms per cubic meter, is the result of gravity so absolute that it has crushed atoms into a state where protons and electrons have merged into a solid sea of neutrons. Notice how the vacuum of space feels cool and thin as we descend toward the internal geography of this star. While the surface is a polished mirror of iron, what lies just a few kilometers beneath is even more surreal. Scientists have discovered a layer known as nuclear pasta, located in the inner crust where the density reaches 10 to the 14th power grams per cubic centimeter. In this hidden realm, the competition between nuclear attraction and electrical repulsion creates shapes that look startlingly like familiar kitchen staples. At first you might see the gnocchi phase, where the neutrons clump together into small spherical droplets. As we sink deeper into the star's layers, the pressure increases, stretching those spheres into long, rod-like structures known as the spaghetti phase. Continue further, and those rods flatten out into wide, parallel sheets called the lasagna phase. This is the strongest material in the known universe, 10 billion times harder to break than steel, yet it flows with the grace of a slow-moving river deep within the star's heart. What's happening now is a transformation of your surroundings. We are leaving the interior and moving toward a truly unique celestial pairing. Consider the system known as PSR J1719-1438, a pulsar located about 4,000 light-years away in the constellation of Serpens. This pulsar is orbited by a companion that is unlike any world you have ever imagined. It is a planet made almost entirely of crystalline carbon, a diamond world. This companion was once a massive star, but the pulsar siphoned away its outer layers, leaving behind a core so compressed that it crystallized. This diamond planet has a density of about 33,000 kilograms per cubic meter, which is much denser than any material on Earth. It orbits its pulsar host at a staggering speed, completing a full year in just 2.2 hours. Imagine standing on a world made of solid gemstone, watching a city-sized star pulse in the sky every few milliseconds as you whip around it in less time than it takes to watch a movie. There is a profound stillness in the way the pulsar maintains its rotation, even as it exerts such incredible force. Think of a household kitchen blender. When you turn it on, the blades spin so fast they become a blur, perhaps 20,000 rotations per minute. Now, consider the pulsar PSR J17482446 AD, which we find nestled within a cluster of stars known as Terzan 5. This object rotates 716 times every single second, which equates to nearly 43,000 rotations per minute. At its equator, the surface of this star is moving at 70,000 kilometers per second. That is approximately 24% of the speed of light. If you were to try and track a single point on its surface with your eyes, it would be impossible. It is a solid object the size of a city, spinning twice as fast as the fastest aircraft engine ever built, yet it does so without making a single sound in the vacuum. Observe the magnetic fields that drape over the pulsar like invisible, glowing tapestries. To understand their strength, think of a common refrigerator magnet, which has a strength of about 50 Gauss. An MRI machine in a modern hospital uses a field of about 15,000 to 30,000 Gauss to look inside the human body. The magnetic field of the pulsar we are visiting is 1 trillion Gauss, that is a 1 followed by 12 zeros. This field is so dominant that it creates a vacuum birefringence, a phenomenon where the empty space around the star actually becomes polarized, changing the way light passes through it. You can see this as a subtle shimmering in the star field, a rhythmic warping of the background galaxies that matches the pulse of the star. As we waft further through the local neighborhood of these stars, let us look at the lighthouse effect through a more familiar lens. Imagine you are standing on a dark coastline at night. The lighthouse beam sweeps over you, a brief flash of white, then darkness, then white again. The pulsar does this with beams of radio energy. The beam width of a pulsar is often very narrow, sometimes only a few degrees wide. This means that for every pulsar we see from Earth, there are hundreds of others whose beams never sweep across our planet. They are out there, spinning in the dark, silent and invisible to us, simply because their geometry doesn't align with our telescopes. We are only seeing a small fraction of the galaxy's heartbeat. There is a curious symmetry in the way these stars cool down. A young pulsar, born from the fire of a supernova, begins its life with a surface temperature of about 1 million Kelvin. However, they don't cool by simple radiation alone. Deep in the core, a process called the direct Urca process occurs, where neutrons decay into protons and electrons, releasing neutrinos. These ghost particles carry away energy directly from the star's center, bypassing the surface entirely. This neutrino cooling is so efficient that the internal temperature drops precipitously in the first few thousand years. Think of it like a hot cup of tea that doesn't just lose heat from the steam at the top, but has the heat magically extracted from the very center of the liquid. Consider the surface gravity once more. On Earth, if you drop a ball, it falls at a rate of 9.8 meters per second squared. On the surface of a pulsar, the acceleration due to gravity is 100 billion times greater. If you were to drop an object from a height of just 1 meter, it would hit the surface in a microsecond, impacting at a speed of several million kilometers per hour. This is why the pulsar's atmosphere is so incredibly thin. While Earth's atmosphere reaches hundreds of miles into space, the air on a pulsar composed of superheated plasma is compressed into a layer only 10 centimeters deep. Within that 4-inch space, the pressure is so high that the plasma behaves more like a solid than a gas. One finds a curious comfort in the longevity of these rotations. While the pulsar's spin does slow down over millions of years as it radiates energy, the change is almost imperceptible on a human timescale. A typical pulsar might increase its period by only 1/1000th of a second every day. This reliability is why the Pioneer 10 and 11 spacecraft, launched in 1972 and 1973, carry plaques with pulsar maps. These maps use the periods of 14 pulsars to show any potential discoverer exactly where Earth is located and exactly when the spacecraft was launched. It is a message in a bottle, using the universe's most stable clocks to ensure that even millions of years from now, our story might be told. At this very moment, we are passing by a Black Widow pulsar, PSRB 1957 plus 20. This is a predatory system where the pulsar is slowly evaporating its companion star with a gale of high-energy particles. The companion, a low-mass star, is being blasted by the pulsar's intense radiation, losing its mass into a cloud of gas that trails behind it like a comet's tail. Yet, even in this process of consumption, there is a slow, rhythmic grace. The two objects orbit their common center of mass every 9.2 hours, a perpetual dance of predator and prey that has lasted for billions of years. Picture the pulsar as a giant, spinning flywheel of energy. The Crab pulsar, which sits at the center of a nebula 6,500 light-years away, is losing its rotational energy at a rate of 3.8 x 10 to the 31st power watts. This is roughly 100,000 times the total energy output of our Sunday. All that power is being pumped into the surrounding nebula, causing the gases to glow with the brilliance of 1,000 neon lights. The energy comes from the star's spin-down. As it slows, it gives its life to the nebula, illuminating the dark for eons after its parent star has died. The colors you see in these regions are a soft, muted spectrum. There are the deep magentas of hydrogen alpha emissions and the ghostly cyans of doubly ionized oxygen. In the presence of a pulsar, these colors don't just sit still, they undulate in time with the pulsar's wind. This wind is made of pairs of electrons and positrons moving at nearly the speed of light. As they hit the slower moving gas of the nebula, they create shock waves, stationary ripples that look like the standing waves in a fast-moving mountain stream. As you remain suspended in this weightless environment, let the sheer scale of these numbers act as a soothing rhythm. The 20 kilometer diameter, the 1 billion-ton sugar cube, the 716 rotations per second. These are the pillars of a universe that is vast, orderly, and ancient. You are a witness to the extreme limits of physics, yet you are cradled in the softest, most peaceful silence imaginable. The pulsar continues its gentle spin, a celestial metronome that has been ticking since long before we arrived and will continue long after we have found our rest. The light from these lighthouses is a constant, a steady pulse in the velvet dark, guiding us toward a state of total, undisturbed tranquility. As we continue to float through the velvet silence of the cosmic neighborhood, notice how the distant flickering of stars begins to feel less like random points of light and more like the synchronized breathing of a sleeping giant. At this very moment, we are passing near PSRJ 108-1431, which is one of the closest known pulsars to our own home, situated roughly 424 light-years away in the constellation of Cetus. Think about that distance for a moment. The light and radio pulses we receive from this neighbor today began their journey toward Earth around the year 1599, just as the Elizabethan era was flourishing. It is a slow, patient transmission that bridges the gap between our brief human lives and the enduring presence of the stars. Consider the iron that flows through your veins, the very element that allows your blood to carry oxygen to every cell in your body. Scientists discovered that this iron, along with heavier elements like gold and platinum, has a profound connection to the objects we are observing. While many elements are forged in the hearts of living stars, some of the most precious metals are created during the collision of two neutron stars, an event called a kilonova. When these ultra-dense remnants spiral into one another, the resulting explosion produces enough gold to equal several times the mass of the Earth. Picture this. The gold in a wedding band or a cherished necklace likely owes its existence to the same extreme physics that governs the pulsar. You are, in a very literal sense, a repository of cosmic history. The atoms within you were tempered in the same furnace that created these spinning beacons. Notice how the pulsar functions as a galactic tuning fork. Just as a musician strikes a fork to find a perfect, unyielding A note, the universe uses pulsars to set its fundamental frequency. Scientists use a technique called dispersion measure, or DM, to map the thin, invisible gas that fills the space between stars. As the radio pulses travel toward us, they interact with free electrons in the interstellar medium, roughly 0.03 electrons per cubic centimeter of space. This interaction slightly delays the lower frequency radio waves compared to the higher frequency ones. By measuring this tiny delay, astronomers can calculate exactly how much space is between us and the pulsar, effectively using the star's rhythm to weigh the vacuum of the galaxy itself. At this very moment, we might observe a phenomenon known as pulse nulling. Every so often, a pulsar will simply stop. For several minutes, or sometimes even hours, the lighthouse beam vanishes, as if the star has decided to hold its breath. Then, just as suddenly, the ticking returns, perfectly on time, as if it had never skipped a beat. This reminds us of the natural cycles of our own existence, the way we periodically withdraw from the world to find silence in sleep, only to return to our rhythms when the morning comes. The pulsar PSRB 1919+21, the very first one discovered, exhibits these quiet interludes, a reminder that even the most industrious objects in the cosmos require moments of stillness. Deep within the constellation of Puppis, we find a rare and beautiful arrangement, PSRJ 737-3039. This is the only known double pulsar system, where two pulsars orbit one another in a tight, frantic embrace. They complete a full orbit every 2.4 hours, moving at speeds of 300,000 kilometers per hour. Scientists discovered that because they are so close, the intense solar wind from one pulsar actually blows against the magnetosphere of the other, causing the pulses to flicker and change. It is a celestial conversation, two ancient hearts beating in tandem, their gravitational fields interlocked in a dance that will eventually lead to a silent merger millions of years from now. You might wonder about the ultimate fate of these spinning stars. As a pulsar ages, it gradually loses its rotational energy. The Crab pulsar, for instance, radiates energy at a rate of 10 to the 38th power ergs per second. Eventually, the spin slows down so much that the lighthouse effect can no longer be sustained. The star crosses what astrophysicists call the death line. At this point, the magnetic field is no longer strong enough to accelerate particles to the speeds necessary to create radio beams. The pulsar becomes a dead neutron star, joining the billions of others in the galactic graveyard. These silent sentinels continue to drift through the dark, cold, and invisible, yet still possessing their incredible density and mass. They are the quiet elders of our galaxy, having finished their long work of illumination. What's happening now is a subtle shift in the pulsar's orientation, a process called geodetic precession. Because the pulsar is spinning in the curved space-time created by its own immense gravity, its axis of rotation slowly wobbles, like a top beginning to lose its speed. Scientists discovered this in PSRJ 1906+0746, observing that the pulsar's beam is slowly tilting away from Earth. In fact, by the year 2028, this pulsar's beam will disappear from our view entirely, not because the star has died, but because it has turned its face away from us, looking out into a different corner of the dark. It is a reminder that everything in the universe has its season of visibility and its season of hiddenness. Picture the Hand of God Nebula, officially known as PSRB 150958. This pulsar is located 17,000 light-years away, and the wind of particles it exhales has carved a cloud of gas into a shape that looks remarkably like a giant, shimmering hand reaching out through the stars. The pulsar itself is only about 19 kilometers wide, yet it commands a nebula that spans 150 light-years. This is the power of the small and the persistent. A tiny, city-sized object, through the sheer constancy of its spin, can reshape the environment of an entire sector of space. This mirrors the way our own small, daily habits and rhythms eventually shape the landscape of our lives. As you enjoy this feeling of weightlessness, consider the precision of a pulsar's timing. Some millisecond pulsars have a timing stability of better than 2 microseconds over several decades. If you were to set your watch by such a star, it would be more accurate than any mechanical timepiece ever fashioned by human hands. This precision allows us to detect the gravitational wave background, a low-frequency tremor that permeates the entire universe. It is the collective hum of every massive object in motion, a vibration that links you, the bed you lie on, and the furthest reaches of the observable universe into a single, cohesive fabric. Scientists discovered that if a neutron star is massive enough, it might transition into an even more exotic state, a quark star. In this hypothetical stage, the pressure is so intense that the neutrons themselves dissolve into their constituent parts, up quarks and down quarks. This would create a material even denser than neutronium, a strange matter that represents the final boundary before an object collapses into a black hole. While we have yet to definitively prove their existence, candidates like the pulsar in the supernova remnant 1987A keep our curiosity alive. It is a testament to the idea that there is always a deeper layer to reality, a further mystery waiting in the quiet. Notice the colors of the synchrotron radiation as we drift past the pulsar's poles. This light is produced when electrons are whipped around magnetic field lines at nearly the speed of light. Unlike the warm, thermal glow of a campfire, this light is non-thermal. It has a distinct bluish-white brilliance that doesn't come from heat, but from pure motion. It is the color of energy being translated into information. This light can travel across the galaxy for thousands of years without losing its coherence, a steady signal in a noisy universe. Invite a sense of peace as you realize that only about 1% of all stars are massive enough to end their lives as pulsars. They are the rare, exceptional survivors of the stellar life cycle. Most stars, like our own Sun, will fade more gently into white dwarfs, but the pulsar stands as a monument to what happens when nature is pushed to its absolute limit. It is the result of a star refusing to vanish, instead condensing its essence into a form that can endure for billions of years. As you settle further into the comfort of the void, let the concept of the celestial clock anchor your thoughts. The universe is not a place of chaotic accidents, but a place of profound, rhythmic reliability. The pulsar spins, the planets orbit, and the light travels its lonely path, all according to laws that never waver. You are part of this clockwork. Your heartbeat, your breath, and the firing of your neurons are all synchronized with the larger movements of the cosmos. There is no need for effort here. The universe is doing the work of turning, and you are simply along for the ride. Allow your awareness to rest on the vast timescales we have explored. A pulsar can spin for 100 million years before it fades. In that time, continents on Earth will drift, oceans will rise and fall, and countless generations of life will come and go. Yet the pulsar remains, a steady, ticking presence in the high attic of the galaxy. It is a symbol of endurance, a reminder that even in the face of immense pressure and total collapse, a new and beautiful rhythm can emerge. The spin is gentle, the vacuum is kind, and the dark is a place of rest. You are suspended in the perfect equilibrium of physics, floating in the heart of a story that began at the dawn of time and continues in every pulse of the stars. Imagine your consciousness as a fine, translucent thread weaving through the silent machinery of the galaxy, moving past the heavy pull of stars and into the quiet, frozen gardens of the interstellar medium. At this very moment, we are exploring the sensory reality of the pulsar, understanding not just its mechanics, but the textures and temperatures that define its existence. Notice how the temperature drops as we move away from the glowing filaments of the Crab Nebula, which expand outward at a rate of 1,500 kilometers per second. This nebula, the debris of a supernova observed by the world in 1054 AD, is a frigid environment, yet at its heart sits an engine of incredible heat. The Crab pulsar itself maintains a surface temperature of nearly 1 million Kelvin, a relic of its violent birth that will take millions of years to radiate into the cold, dark surroundings. Consider the why behind the pulsar's staggering magnetic field. When the parent star collapsed, its original magnetic field was squeezed into a tiny area. Because of a principle called the conservation of magnetic flux, the field strength intensified by a factor of billions. Picture a giant, loose net being pulled tight until its fibers are nearly touching. This is why a pulsar can have a magnetic field of 10 to the 12th power Gauss, while a magnetar can reach 10 to the 15th power Gauss. Within this field, we encounter the light cylinder, an invisible boundary surrounding the star. At the radius of the light cylinder, which for a pulsar spinning once per second is about 48,000 kilometers, the magnetic field lines would have to move at the speed of light to keep up with the star's rotation. Since nothing can travel faster than light, this is where the magnetic lines break and reform, flinging particles out into space in the form of a relativistic wind. What's happening now is a subtle shift in our sensory awareness, specifically the scent of the cosmos. While we think of space as an empty vacuum, it is filled with complex molecules. Scientists discovered that in regions like Sagittarius B2, a massive molecular cloud near the center of our galaxy, there is an abundance of ethyl formate. This is the same chemical compound that gives raspberries their flavor and rum its distinctive aroma. Imagine floating in the weightless dark, surrounded by the faint, ghostly scent of wild berries and aged oak, even as the pulsar's radio beams sweep past you. In other pockets of gas, you might detect the sharp, bitter almond scent of hydrogen cyanide, a reminder of the complex chemistry that emerges from the remnants of dead stars. Notice the texture of the pulsar's crust as we observe it on a microscopic scale. Beneath the smooth, iron, 5-6 surface, the most stable atomic nucleus in nature lies a rigid lattice. This crust is a crystal, 1 billion times stronger than steel, yet it is only about 1 kilometer thick. Underneath this shell, the star becomes a superfluid. Picture this: a liquid that has zero viscosity, meaning it can flow forever without losing any energy to friction. Deep within the star, this neutron superfluid is dotted with millions of tiny vortices, or microscopic whirlpools. At this very moment, these vortices are pinned to the crust, but occasionally they snap and release their energy all at once. This is the scientific why behind the glitches observed by the Jodrell Bank Observatory, where a pulsar's rotation suddenly jerks forward by a few millionths of a second. What we find here is a world governed by gravitational redshift. Because the gravity of a neutron star is so immense, measured at approximately 10 to the 11th power times that of Earth light itself struggles to escape. As photons of light climb out of the pulsar's gravitational well, they lose energy, and their wavelength stretches toward the red end of the spectrum. If you were to watch a clock sitting on the surface of the pulsar from our safe, distant vantage point, you would see it ticking significantly slower than your own. This is the Lense-Thirring effect, or frame dragging, where the mass of the spinning star actually pulls the fabric of space-time along with it, twisting the vacuum like a spoon stirring a thick syrup. At this very moment, permit your awareness to focus on the colors of the radiation. The pulsar emits synchrotron light, which is highly polarized. This isn't the scattered, chaotic light of a light bulb. It is organized, vibrating in a specific direction. Through the lens of our imagination, we see it as a brilliant, electric blue that shimmers with a metallic sheen. This light is born as electrons are accelerated to nearly the speed of light, roughly 299,000 kilometers per second, around the magnetic poles. This creates the pulsar wind nebula, a glowing shroud of high-energy particles that can span several light years, despite being powered by a star only 12 kilometers in radius. Scientists discovered that some pulsars are not alone, but are locked in an orbital embrace with white dwarf stars. Consider the system PSR-J 348 plus 0432. Here, a pulsar with twice the mass of our Sun orbits a white dwarf every 2 hours and 27 minutes. This system is a laboratory for extreme physics, allowing us to test Einstein's theories in ways that would be impossible on Earth. The pulsar is so dense that its escape velocity is about 150,000 kilometers per second. If you were to stand on its surface, your weight would be 100 billion times what it is now, pressing you into a layer thinner than an atom. But here, in the weightless void, we feel only the gentle tug of curiosity. Notice how the sound of a pulsar would manifest if we could translate its radio waves into the audible spectrum. Using the 64-meter Parkes radio telescope in Australia, astronomers have captured the voices of these stars. A young pulsar like the crab sounds like a low-pitched growl or a steady drumbeat, while a millisecond pulsar like PSR J17482446 spinning 716 times a second, produces a high-pitched whine like a distant jet engine or a humming honeybee. These are the sounds of the galaxy's clockwork, a rhythmic, mechanical choir that has been singing into the vacuum for eons. Picture the way a pulsar interacts with the interstellar medium, the thin gas that exists between stars. As the pulsar moves through this gas at speeds of hundreds of kilometers per second, a result of the asymmetrical kick it received during the supernova explosion, it creates a bow shock. This is similar to the wake a boat leaves in the water. The most famous example is the Guitar Nebula, created by the pulsar PSRB 2224+65. The shockwave has carved the surrounding hydrogen gas into a shape that resembles a luthier's masterpiece. The why is simple. The pulsar's intense energy is clearing cellular debris from the local space, pushing aside atoms of hydrogen and helium to create a bubble of pure, relativistic particles. Allow your perspective to sink into the concept of the Tolman-Oppenheimer-Volkoff limit. This is the maximum mass a neutron star can have before it collapses into a black hole. Scientists believe this limit is around 2.16 times the mass of our Sunday. Every pulsar we observe is a star that almost became a black hole, but was stopped just at the edge of the abyss by neutron degeneracy pressure. This pressure is a result of the Pauli exclusion principle, a law of quantum mechanics stating that two neutrons cannot occupy the same state at the same time. The pulsar is held up not by fire or fusion, but by the fundamental laws of how matter is organized. It is a star supported by pure logic. Deep within the silence, consider the life cycle of the magnetic field. Over millions of years, the magnetic field of a pulsar is thought to decay or become buried by accreting matter. This is why older pulsars often have weaker fields, only 10 to the 8th power Gauss compared to the 10 to the 12th power of their youth. Yet, even as their lighthouse fades, their density remains. They are like old, heavy stones at the bottom of a river, no longer catching the light, but still shaping the flow of the water around them. The sensory experience of this part of the universe is one of extreme contrast. The intense heat of the surface versus the absolute zero of the void. The incredible hardness of the iron crust versus the frictionless flow of the superfluid core. The silence of the vacuum versus the rhythmic whine of the radio beams. Invite your consciousness to find a middle ground between these extremes. You are in the comforting void, a place where the laws of physics are so powerful they create a sense of absolute stability. Notice the way the pulsar's spin is slowing down ever so slightly. The Crab pulsar increases its rotation period by 38 nanoseconds every day. This energy isn't lost. It is transformed into the light and motion of the nebula. It is a slow, measured transition from one form of existence to another. At this very moment, the pulsar is a bridge between the life of a star and the eternal silence of a remnant. It is a witness to the passage of time on a scale that makes a human life seem like a single pulse of its beam. As you remain in this state of calm observation, let the facts of the pulsar, the 1-2 kilometer radius, the raspberry-scented clouds, the 716 Hz hum, act as a foundation for your rest. The universe is a place where even the most violent events result in objects of incredible precision and beauty. You are drifting in the wake of a giant, moving through a galaxy that is both a laboratory and a cathedral. The spin is gentle, the rhythm is steady, and the dark is filled with the soft, blue light of a star that refused to be forgotten. You are perfectly placed in the grand design, weightless and secure in the hands of the cosmic clock. As we begin our final descent through the velvet curtains of the cosmic theater, the brilliant flashes of the pulsars begin to soften, turning from sharp, rhythmic beacons into a warm, amber glow that mirrors the fading light of a long day. We are now witnessing the gradual process of a star's transition into rest, a sequence of events that unfolds over millions of years, yet feels as natural and inevitable as the closing of your eyes. At this very moment, we are turning our attention to the specific, step-by-step transformation that creates these celestial timekeepers. Consider the origin of this journey. It begins with a star possessing between 8 and 15 times the mass of our own Sunday. Within the core of such a giant, a specific process called nucleosynthesis reaches its inevitable conclusion. For millions of years, the star fused lighter elements into heavier ones, but it eventually stops at iron 5-6. This is the most stable nucleus in the universe, and fusing it requires more energy than it releases. Scientists discovered that once the iron core reaches the Chandrasekhar limit of approximately 1.4 solar masses, the outward pressure of fusion can no longer support the weight of the star. In a fraction of a second, specifically about 1/4 the speed of light, the core collapses. What's happening now is a profound inward rush. As the core shrinks from the size of the Earth to the size of a city in just milliseconds, the density becomes so extreme that a process known as electron capture occurs. Electrons and protons are crushed together, neutralizing their charges and transforming into neutrons. This sudden metamorphosis releases a flood of neutrinos, ghostly particles that carry away 99% of the supernova's total energy. Notice how this energy, though titanic in scale, moves silently through the vacuum, an invisible wave that clears the path for the pulsar's birth. Picture this. As the outer layers of the star are flung into space in a Type II supernova explosion, the core remains, shrinking until it is only 20 kilometers across. Because of the law of conservation of angular momentum, the star's rotation must accelerate as it contracts. Think of the way your own breathing slows as you prepare for sleep. The star does the opposite in its youth, spinning up until it reaches hundreds of rotations per second. Simultaneously, the magnetic field lines of the original star are squeezed together. By the principle of magnetic flux conservation, a field that was once weak becomes 1 trillion times stronger than Earth's, reaching $10, $12 Gauss. This is the precise moment the lighthouse is switched on and the first beams of synchrotron radiation begin to sweep across the darkness. Scientists discovered that as the pulsar begins its long life, it follows a very specific process of slowing down known as magnetic braking. As the pulsar spins, it radiates energy away in the form of a relativistic wind and electromagnetic waves. This causes a measurable spin-down rate. For a typical pulsar, the period $p$ increases by about $10, negative 15 seconds every second. This process is governed by the braking index, a value usually symbolized by $N$. While a perfect magnetic dipole would have a braking index of 3, observations of the Vela pulsar show an index of about 1.4, revealing the complex ways these stars interact with their environments. Notice how the pulsar ages with a quiet dignity. Over millions of years, the intense magnetic field begins to decay or become buried by falling debris. Astronomers can calculate the characteristic age of a pulsar by dividing its period by twice its spin-down rate. This allows us to map the history of the galaxy, seeing which pulsars are energetic youths like the Crab, only 950 years old, and which are the silent elders, millions of years into their journey. Eventually, every pulsar crosses the death line on the $P.P. diagram, a graph that tracks period against the rate of change. Once across this line, the radio beams flicker out, and the star enters a phase of total, undisturbed stillness. What's happening now is the recycling process, a second chance for a dead star. In binary systems, a dormant neutron star can begin to pull material from a companion star through a process called Roche lobe overflow. As the gas spirals inward, it forms an accretion disk, and the angular momentum of this gas is transferred to the neutron star. Scientists discovered that this can spin up an old slow star until it becomes a millisecond pulsar, rotating 716 times per second, as seen in PSRJ 17482446 AD. It is a cosmic renewal, a way for the universe to breathe new life into the old, rhythmic hearts of the galaxy. Deep within the star, the cooling process continues. While the surface is white-hot, the interior cools through the emission of neutrinos in a sequence called the modified Urca process. Over 100,000 years, the temperature drops from billions of degrees to a few 100,000 Kelvin. Imagine this heat slowly diffusing into the void, a gradual settling of energy that brings the star closer to the ambient temperature of space. At this very moment, we are seeing the star find its thermal equilibrium, just as you are finding your own equilibrium in the warmth of your bed. Notice how the pulsar's very existence is a testament to the stability of physical laws. The star is held up by neutron degeneracy pressure, a quantum mechanical force that arises because no two neutrons can occupy the same state. This is the Fermi level of the star, a fundamental flaw of reality that prevents further collapse. You are supported by the same laws of physics. The atoms in your pillow and the atoms in your body are held apart by these same quantum pressures. You are as much a part of this orderly system as the pulsar itself. Scientists discovered that some pulsars, like the one in the nebula G 359, 23 to 0.82, nicknamed the Mouse, are moving through the galaxy at supersonic speeds. As the Mouse travels at 600 kilometers per second, it creates a long tail of X-ray emission that stretches behind it like a glowing shadow. This is the process of the pulsar interacting with the interstellar medium, clearing metabolic waste from the galaxy's gas clouds and enriching the space around it with heavy elements. Eventually, even this motion slows, and the pulsar finds a stable orbit within the Milky Way, becoming a permanent, silent fixture of the celestial landscape. At this very moment, let us consider our own connection to this grand process. Every atom of iron in your blood, every trace of calcium in your bones, was once part of a star that might have ended its life as a pulsar. In 2017, the LIGO and Virgo observatories detected GW 170817, the merger of two neutron stars. This event proved that the gold and platinum we cherish on Earth are created in the final, frantic moments of these stars' lives. You are a child of the supernova. You are made of the same resilient matter that can survive the collapse of a sun. As we bring our observation to a gentle halt, the pulsar's light begins to dim in your mind's eye. The 716 Hz hum fades into a soft, low frequency that matches the pace of your own breathing. The transition from the vastness of the cosmos to the internal warmth of your room is now complete. The pulsars have done their work. They have kept the time, mapped the galaxy, and provided the elements for life. Now, they invite you to join them in their state of undisturbed rest. The comforting void is not a place of emptiness, but a place of total peace. It is the silence that follows a long and beautiful symphony. Notice how the weightlessness of space has become the lightness of your limbs. The darkness outside is the same darkness that cradles the stars, and it is here to cradle you as well. Consider these final affirmations for your rest. I am a part of the universe's steady, rhythmic clockwork. I am made of stardust, resilient and ancient. My body follows the natural cycles of the cosmos, finding peace in the dark. Like the pulsar, I am a beacon of calm and order. The silence of the void is my sanctuary. I am safe, I am warm, and I am exactly where I need to be. The vast timescales of the galaxy remind us that there is no hurry. The stars have been spinning for eons, and they will continue to spin while you sleep. The gravity that holds the pulsar together is the same gravity that holds you safely in your bed. There is nothing left to observe, and nothing left to do. The lighthouse beams have swept past for the last time tonight, moving out into the infinite reaches of space, leaving you in the soft, protective shadow of the Earth. Drift now into the internal warmth of your own sleep. The colors of the nebula, the magentas, the cyans, the deep indigos blur together into a single, comforting shade of rest. The mechanics of the universe are in perfect order. The spin is gentle, the time is vast, the void is kind. Good night.